Have you ever looked at a massive building or a super tall tree and just thought, how in the world would I even start to measure that? Well, it turns out geometry has these awesome little shortcuts. Today, we're going to unlock a really simple trick that lets you measure pretty much anything just by using a little bit of math. Let's get into it. So picture this. You're standing in front of this giant flagpole. You can't climb it, you definitely don't have a huge measuring tape, but you notice it's casting this long shadow on the ground. So the question is, could you actually figure out its exact height using just that shadow? It sounds like a riddle, right? But believe it or not, this is a real problem. And the solution is surprisingly simple. All you need is the right tool from your geometry toolbox, and this whole thing goes from seemingly impossible to a pretty straightforward puzzle.
So what is this magic tool? It's called the angle-angle similarity theorem. Now don't let the fancy name scare you off. Just think of it as a geometry hack, a major shortcut for understanding shapes. This is the key that's going to unlock our flagpole problem.
Okay, so the rule itself is actually super simple. All it's saying is this. If you've got two triangles and you can find just two angles that match up between them, then you automatically know those triangles are similar. What that means is they're the exact same shape, just scaled up or down. You know, like a perfect little model of the bigger one.
I like to think of it kind of like a lock that needs two keys. You find one matching angle, that's your first key. Then you find a second matching angle, that's your second key. And once you've got both keys in the lock, click, you've unlocked it. You've proven the triangles are similar, and now you can do all sorts of cool stuff with that info.
Okay, so theory is one thing, but let's actually see how this works. We're going to head to the practice range and put this angle-angle theorem to the test with a few different examples, just to see it in action.
All right, first up, take a look at these two triangles. Are they similar? Remember the mission. We're hunting for just two pairs of matching angles. Take a look. See them anywhere?
Okay, let's break this down. First up, the easy one. See that little square symbol in the corner? That means they both have a 90-degree right angle. That's our first A. Bam! Now for the second. We know that all the angles in a triangle have to add up to 180 degrees. So in that first one, we take 180, subtract the 90, subtract the 26, and we get 64 degrees. And what do you know? The second triangle has a 64-degree angle right there. That's our second A. We've found two matches, so yep, these are definitely similar.
Let's try another one that looks a little different. Here we have a smaller triangle kind of tucked inside a bigger one. So, how in the world are we supposed to find two matching angles in this setup? So, the first matching pair is a little sneaky. See angle A up at the top? It's literally the same angle for both the little triangle and the big one. So of course they match. That's one. Then the problem just tells us straight up that angle ABE and angle C are both 52 degrees. Well, that's our second match. We've got two pairs, so we just proved that the little triangle ABE is similar to the big one, ACD.
All right, one last practice puzzle. Here we've got two triangles that form this kind of bow tie shape, and we're told that the top and bottom lines are parallel. And that right there, that's a huge clue. So where are our two matching angles hiding? This is a perfect example of two classic geometry rules you might remember. First, look right in the middle, at point V. See how the angles across from each other look like a mirror image? Those are called vertical angles, and they are always equal. Boom, there's our first pair. Second, because those top and bottom lines are parallel, you can actually trace a Z shape. And the angles tucked into the corners of that Z, angles S and U, they're called alternate interior angles, and they are always a perfect match. So there you go, two pairs found. These triangles are similar.
All right, we've been to the practice range. We've got our tools sharpened. Now it's time to go back to that flagpole. It's time to take this math concept and use it to solve a real-world problem.
So check this out. That real-world scene on the left and the geometry diagram on the right, they're the exact same puzzle, just drawn differently. The flagpole and its shadow make a big triangle, and the woman and her shadow make a smaller, similar one.
So how do we know they're similar? Well, let's use our angle-angle theorem. First off, both the woman and the flagpole are standing straight up, right? So they both make a 90-degree right angle with the ground. There's our first A. Second, because the sun is so incredibly far away, its rays are hitting the ground at the exact same angle for both the woman and the flagpole. And that's our second A. We've just proven the two triangles are similar. And this is where the magic happens. Because we know those triangles are similar, it means the ratio between their sides has to be identical. So we can set up what's called a proportion. The flagpole's unknown height, let's call it x, divided by the woman's height has to equal the flagpole's shadow divided by the woman's shadow.
This table lays it all out nice and clean. From here, it's just some simple math. All we do is cross-multiply. So 40 times x equals 64 times 50. That gives us 40x equals 3,200. We just divide both sides by 40 to get x by itself, and we get our answer. X equals 80.
And there it is. The flagpole is 80 feet tall. No climbing, no giant tape measure, just shadows and a little bit of geometry. How cool is that?
So you've just unlocked this incredibly powerful new tool. You've seen how it works, you've seen what it can do, and now it's your turn to start looking at the world just a little bit differently. The thing to remember is, the angle-angle theorem isn't just some abstract rule in a math book. It's a real, practical tool that lets you measure the height of pretty much anything that casts a shadow. A tree, a building, a streetlight, anything.
So, I'm going to leave you with a little challenge. Next time you're outside on a sunny day, find a tall tree, look at its shadow, and look at your own. You've got a tape measure. What two simple measurements could you take right there on the ground to figure out exactly how tall that tree is? The answer is literally right at your feet.